Here we're looking at section 9.5 and we're continuing to look at those ratios in our right triangles. In this lesson we're going to be using the sine and cosine ratios. Then we're going to be finding the sine and cosine of angle measures in special right triangles. Right, and these special right triangles are our 30, 60, 90s or our 45, 45, 90 triangles. Then we're going to be solving some real life problems involving the sine and cosine ratios. So again, here's our sine and cosine ratios, but I want to write up at the top this thing that I've always known, and this is how I remember is SOHCAHTOA. This can help a lot, and we talked in the last video about this TOA. This is the tangent is the opposite over adjacent. Now here I'm going to be looking at this first part, so this helps me remember the order that things go in. So I know that sine is the opposite over the hypotenuse and that cosine is the adjacent over the hypotenuse. This is just something that helps me remember so I don't have to memorize every single thing all the time. So again, I'm looking at my right triangle and I'm going to look here at this angle A. And the leg that's adjacent, right, the one right next to it, the leg that's opposite, it's totally across from it, and the hypotenuse, always across from my right angle. So I'm finding the sine of A. Since I know that sine is the opposite over the hypotenuse, I would use the opposite over the hypotenuse here. Cosine is a little bit different. Cosine is my adjacent over the hypotenuse. So the cosine of A would be this blue one, AC, over the hypotenuse. So now let's see this in action. So here we're asked to find the sine of S, the sine of R, the cosine of S, and the cosine of R, and write each as a fraction and as a decimal. So the first thing I'm going to be doing is finding the sine of S. And I always, at the top of my page, write out my SOHCAHTOA to help me remember what I'm actually looking at and looking for. So I know I'm looking for the sine of S, so here's my angle S. I'm going to be looking at the opposite and the hypotenuse. So again, I can write that as my fraction, 63 over 65, and that's approximately my decimal approximation. So now I'm looking at the sine of angle R. So here is angle R, and I'm looking for my opposite over hypotenuse, and I can find that there. So now let's look at cosine. So cosine I know of S, CAH, the adjacent side over the hypotenuse. So here's my fraction there. And then the cosine of my angle R is here, 63 over 65. One thing I really want you to notice, and we're going to talk about this in just a minute, but do you see how my sine of S is the same as my cosine of R, right? Because I've got my 63 over 65 and I've got my 63 over 65. You'll also notice that the sine of R is the same as the cosine of S. Here we go, and here we go. And one thing I know about R and S is that angle R is complementary, right, to angle S. And I know that these two angles, when I add them, because I add R plus S equals 90 degrees. And I know that because I'm dealing with a right triangle, and all triangles have a sum, have a total of 180 degrees, and 90 of it's here, so I know that these two added equals 90. Because of that fact, I know that the sine of one is equal to the cosine of the other one. So keep that in mind as we continue on. So here's what this is talking about actually in our core concept, the sine and cosine of our complementary angles. So A and B are my complementary angles, and I know that because I'm dealing again with my right triangle. So I've got my A, my C, and my B. And we generally think of C as being the right angle. So I know that the sine of A is equal to the cosine of 90 degrees minus A, which is equal to the cosine of B, which we showed in that last slide. So the sine of one angle is equal to the cosine of its complement. That's one way we can say it. So if I'm looking at the sine of A, I know it's equal to the cosine of B. The cosine of A is equal to the sine of B. We kind of want to think of them back and forth, sine and cosine, right? And that's just written here. So you can write this out however will make sense to you. But to me, this 90 to minus A just tells me the other angle in my triangle. That's what this 90 minus A means, is they are complementary angles. So here's my example. So write sine of 56 degrees in terms of cosine. So first I have to find what its complementary angle is, right? So first I do that. I find the sine of 56 is equal to 90 minus that 56, and I know that that's 34 degrees. I could also draw this out as a triangle, right? So if I've got my triangle and I know that this is my 90 degrees If this is 56 degrees right up here, that means that I can find this by just doing my 90 minus 56, which is 34. So that's another way. We're doing the same thing. Sometimes just having a picture makes it a little bit more realistic and easier to follow. So now here we have multiple things that we need to find. I have to find the values of x and y using my sine and cosine and round each answer to the nearest tenth. So one thing I notice is here I'm given an angle and I'm given the hypotenuse, so that right away tells me I'm going to be using sine or cosine. So to find x, I see that I'm using the opposite and the hypotenuse. So again, at the top of my page, I can write out SOHCAHTOA. Okay? And so this can help me figure out what I'm looking at as well. So I'm going to be using the sine ratio to find x because I'm dealing with the opposite side and the hypotenuse. And I see here's the opposite and hypotenuse, so I know I want to use sine. So now I just write out my ratio. So I know the sine of 26 degrees equals the opposite over the hypotenuse. I substitute the things that I know. Then to get x by itself, I multiply both sides by 14. Then I end up with 14 times the sine of 26 degrees. And here's what I just put in my calculator. So now that x equals approximately 6.1. So now I have to find the value of y. So to find the value of y, I want to use the cosine because I'm still given this 26 and I'm given this 14. And I see that I have the adjacent side and the hypotenuse. So I'm going to use my cosine ratio. So I know the cosine of 26 degrees equals the adjacent over the hypotenuse. I substitute the things that I know, multiply both sides by 14 to get this out of the denominator, and I use my calculator. So the value of y is about 12.6. So now I always want to go back and just make sure that that makes sense as a triangle. If one side is 14, the other side is about 6.1 and the other side is about 12. That makes sense to me, and that does actually form my triangle, so I know I was right finding those side lengths. So now here's a chance for you to practice using the sine and cosine. The first thing you always want to do is at the top of your paper, SOHCAHTOA. This helps you, especially when we have triangles like this one, helps you figure out, am I dealing with sine? Am I dealing with cosine? What about the tangent? Which one fits in there? So what am I going to use? So now try these on your own and see if you can get the correct answers for them. So now here we're going to be using our special right triangles. And I know it's a special right triangle because I'm given this 45-degree angle. So let's see what we can look at. So first I always sketch out my triangle, right? You always draw it first. So I sketch my 45, 45, 90 triangle. And since I'm dealing with a special right triangle, I always make my shorter lengths, so in this case my legs, 1. And I know that to get the hypotenuse from a 45, 45, 90 triangle, I multiply the side length by the square root of 2. So I go ahead and I draw out my triangle and label the things that I know. And now I know that I have deal with 45 degrees, that sine is the opposite over the hypotenuse. So I can go ahead and substitute the things that I know. And here's how I can simplify this, right? And I don't like ever having square roots in the denominator. So in order to get rid of that square root in the denominator, I multiply this by the square root of 2 over the square root of 2. And I can do this because this entire fraction equals 1, right? When I divide something by itself, it's 1. And I multiply by the square root of 2 over square root of 2 because that will simplify my denominator because I know the square root of 2 times the square root of 2 gives me 2. And then I multiply my numerator, so I end up with square root of 2 over 2. I always want to simplify and never leave radicals in my denominator. So that tells me the sine of 45 degrees. And then I can go ahead and use my calculator to simplify from there. So now I also have to find the cosine of 45 degrees. So now I'm dealing with the cosine of this angle, and I know that the cosine is the adjacent, so the side next to it, over the hypotenuse. I substitute what I know. Again, I see I have a radical in the denominator, so I multiply by the square root of 2 over the square root of 2, and I end up with square root of 2 over 2, and again I can simplify. And one thing I would have noticed is that the sine of 45 and the cosine of 45 are going to be equal to each other because 45 degrees and 45 degrees are complementary angles. And remember that the sine and cosine of complementary angles are the same thing. So I could have guessed that as well. But here I'm just showing this using my special right triangles. So now I'm going to be using a 30, 60, 90 triangle and finding the sine and cosine of that angle. So the first thing I always do is I draw my triangle, and I label my short leg, and in my 30, 60, 90 triangles, the short leg is always across from the 30. My short leg is 1, my long leg is the square root of 3, and the hypotenuse is 2. This is always true for a 30, 60, 90 triangle. So I always start here. So now I can find the sine of that 30 degrees, right? So I know that sine is the opposite over the hypotenuse. So I deal with the opposite and the hypotenuse. I substitute what I know, and I can find the decimal approximation as well. So now let's find the cosine of that 30 degrees. Well, I know cosine, I use the adjacent side and the hypotenuse, so I end up with square root of 3 over 2. I don't have to simplify anything here because my radical is already in the numerator, so I'm good there. So I can plug this in my calculator and get the decimal approximation of the cosine of 30 degrees. Here, you'll see they're not the same, but I know that 30 degrees is not a complementary angle to 30 degrees, so I knew that they would actually be different here. So now here you have to use our same 30, 60, 90 triangle that we used in the last example and find the sine and cosine of that 60 degree angle instead. So now we're going to look at our kind of real life problems, our real world problems. So you're skiing on a mountain with an altitude of 1,200 feet. The angle of depression is 21 degrees. So the angle of depression is if I'm standing and then I look down, how far down do I look? That's what an angle of depression is. So I always want to draw out my triangle first and label what I know. So I know the altitude of the mountain is 1,200 feet, and I know my angle of depression is 21 degrees. So now I'm trying to find the length of the run. How far will I ski? So the one thing I notice is I have to figure out, am I going to use sine or cosine? So again, I start with SOHCAHTOA. Here I see I'm dealing with the hypotenuse, so it's either going to be sine or cosine. And I see here I have the side length that's opposite the angle, so I'm going to be using sine because this is the only one with the opposite and the hypotenuse. So now let's see what we're looking at. Okay, so I know, and this just talks about what we talked about above. So the sine of 21 degrees equals the opposite over the hypotenuse. I substitute in what I know. Now to get rid of this fraction, I multiply both sides by x. Now to get x by itself, I divide both sides by sine of 21 degrees. Then I put that in my calculator and find that x is approximately 3,348.5. So I ski about 3,349 feet down the mountain. And then I can look back and see, does that make sense? Well, here my elevation, right, my altitude was 1,200 feet. So I'd imagine I would have something quite a bit bigger than that. So my answer makes sense in this context. So I know I'm good. So now look back at that same and see if you can use, draw your own triangle and see what you can do from here. Oh, sorry. See if you can use, draw your own triangle using the same other measurements, but your angle of depression has changed. So find the distance that you ski down the mountain if your angle of depression has changed. So now we're going to look back at our learning targets. First, we had to use the sine and cosine ratios. The big thing to note with these sine and cosine ratios is first figuring out which one am I going to use. And you can determine that based on the side lengths of the triangles that you're given. And then we used our special right triangles, our 45, 45, 90, and our 30, 60, 90 to find the sine and cosine of certain angle measures there. Then I can use this to solve some real life problems using that sine and cosine ratio. Now that we've gone through all these learning targets, now go ahead and work on that homework for 9.5.